Today we're going to continue looking at continuity. We're going to look at the definition of continuity over an open and over a closed interval. So looking at our graph here, it's very easy to see we have 2 points of discontinuity. Here at x equals 1, there is a removable point of discontinuity, and at x equals 2, there's a jump discontinuity. So it's continuous everywhere from 0 to 3 except for those 2 points of discontinuity. So how I'd write my function f of x is continuous, starting at 0, going to 1, then from 1 to 2, and then from 2 to 3. Notice that the values 1 and 2 are not included in my continuity because it's discontinuous there, but my endpoints of 0 and 3 are included. Now let's look at another way this could be done. Here we're given a piecewise function and we're asked to figure out what values of a or b would make this a continuous function. Well, first I look at the pieces that make up this function. I notice that I have a linear equation, our second equation is linear, and my third equation is quadratic. So I know those three functions are continuous everywhere where they're defined. So my only problem that I'm going to have difficulties with is when I put the pieces together. And to fix that, I'm going to use our 3-point definition of continuity. The three requirements for the 3-point definition of continuity: the limit from the left must equal the limit from the right, the limit must exist, the function value must exist, and the limit value must equal the function value. So those are the three things that we're looking for. So I'm going to start at looking at my point x equals -2, and I'm going to evaluate the limit from the left, which would be using the -x minus 3. Now I'm going to set this up so it has to equal the limit from the right. So let's look over here. Let's see our limit as x approaches -2 from the right. We should use the middle equation, so that's going to be ax plus b. And for continuity to occur, this limit, the limit as x goes to -2 from the right of ax plus b, must equal the limit as x goes to -2 from the left. So using direct substitution in this first limit and direct substitution in the second from the right-hand side limit, we'll simplify this down and we'll get an equation that we need to solve for, a and b in. So our first equation is we have -1 is equal to -2a plus b. Now I'm going to use my second point of possible discontinuity at 1, and we're going to set this up so I must have continuous function. So again, I'm looking that the limit from the left of 1 must equal the limit from the right of 1. So if I'm looking at the left of 1, I'm going to use the middle equation, which is ax plus b, and that has to equal the limit from the right of 1, which would be the bottom equation, x squared. Using direct substitution, I end up with the equation a plus b is equal to 1. So now I'm going to take these two equations I just found and I'm going to solve the system equation for a and b. You can do this any method that you want. I'm going to choose to do the elimination method by subtracting the second equation, a plus b equals 1, from the first equation, eliminating our b terms. And then solving for a, and we end up with a is equal to 2/3. Then I'm going to take that a equals 2/3, substitute it into a plus b equals 1. And you should get b is equal to 1/3.
30 seconds remaining.
So now that I know what a and b is, all I have to do is justify using the definition of continuity. So this is the equation I think will give us a continuous function everywhere. So now I'm just going to justify it by checking my 3 points of continuity at our points of division, and the -2 and at the 1.
Ending period 3.
So the limit as x approaches -2 from the left is equal to, when I do direct substitution, 2 minus 1, which is 2 minus 3, which is -1. Now the limit as x approaches -2 from the right, we'll be using our second equation, so that'll be the 2/3 x plus 1/3. Substituting that in, we also get that the limit as x approaches 2 from the right is -1. So I pass the first test. That means the limit as x approaches -2 is -1 and it exists. So now I need to figure out what the function value at -1 is. Function value at -2. And we would use the top equation for that, since that's where -2 is equal to at. And we get -1 as well. So the limit at x approaches -2 is equal to the function value at -2, therefore it's continuous at -2. I'm going to repeat this three-step process for x equals 1. And the limit as x approaches 1 from the left, we would use our middle equation, doing direct substitution. We end up 2/3 plus 1/3, which is 1. And the limit as x approaches 1 from the right would be our bottom equation of x squared. And that is 1 squared, which is also 1. Therefore, the limit as x approaches 1 is 1, and it exists. Then I'm going to figure out my function value. For f of 1, we'd use the bottom equation, which would be 1 squared, which is 1. So the limit as x approaches 1 from the left is equal to our function value of at 1, therefore it's continuous at 1. And again, since all three pieces of the equation were polynomials, so it's continuous everywhere over its domain, I know that this function is continuous everywhere. The only difference with continuous over an open interval and a closed interval is when you look at the endpoint. So the first thing, finding it continuous at every point inside the interval, is the exact same thing as what we just did. That's the same rule for over an open interval. The only thing changes is at the two endpoints of the interval. Now at the smaller interval, which is a, notice that we just look at the limit as x approaches a from the positive side, because there's nothing on the negative side of that graph. There's nothing to the left of a. Everything's to the right of a. And that must equal the function value at a. And then we look at the upper endpoint when x approaches b. We only look at the limit as it approaches from the left, because there's nothing that's happening to the right of b. So we can't say the limit exists on the left and the right. So we only look at that one side, and it must equal the function value at that point. But the procedure is going to be the exact same thing as what we just did for open interval. Except on the endpoints, we only check as it approaches from that side. We don't check the other points. So let's say our example we're going to use here is f of x is equal to square root of 1 minus x squared. This is like a semicircle. That's what this graph looks like. And we're going to discuss the continuity of this graph.
30 seconds remaining.
First, I look at the function. F of x is equal to square root of 1 minus x squared is a rational function. And from that list of all those equations I gave you, all those functions I gave you last time.
Starting period 4.
And from the list of all those equations I gave you last time, we know that a rational function is defined everywhere in which the function is defined. Now, this is a square root, an even root, so I know what's underneath the radical cannot be negative. So I know that 1 minus x squared must be greater than 0. To get greater than, I know that I'm going to have to be between two values. And in order to figure out what is between, I know that the greatest value of this x squared, that x squared needs to be less than or equal to 1, or -1, plus or minus 1. So that tells me when I take the square root of that value, I have negative 1 needs to be less than or equal to x, which is less than or equal to 1. So that's the domain of f of x. And I know from the fact that this is a radical equation of an even radical that it is continuous everywhere, all points of its domain. So that means the only thing I have to check is the endpoints. So part 1 is continuous for every point inside the interval from negative 1 and 1 is true. Now that I figured out its domain. So all it's left to do is figure out, is it continuous at the endpoint? And all I need to do is I need to figure out the limit as x approaches negative 1 from the positive side and see if that limit value is equal to the function value at negative 1. And then I need to check and see on the right, the upper limit, the upper endpoint, that if the limit as x approaches 1 from the left-hand side is equal to f of 1. So to check the continuity at endpoints, let's first look at the left-hand endpoint. And for this to be true, the limit as x approaches negative 1 from the positive side, from the right, must equal the function value at negative 1. So let's see what that's true. So limit as x approaches negative 1 from the right-hand side, I can use direct substitution in this one. I don't have to do any algebra, simplifying the radical. And I end up with 0. So now let's check the function value. F at negative 1. Again, all I have to do is substitute in place of every x negative 1. Simplify that radical, and I end up with 0. So since the function value at negative 1 is equal to the limit as x approaches negative 1 from the right-hand side, it is continuous at this left endpoint. So now let's check the right endpoint. So this time I'm going to look at the limit as x approaches 1 from the left-hand side, so there's nothing past 1, of our function, and I need to compare that to the function value at 1. So plugging in from the left of 1, I can use direct substitution, and I end up that limit is equal to 0. Plugging in 1 into my function, I also end up with the function is equal to 0. So since the limit as x approaches 1 from the left is equal to the function value at 1, it is continuous at the right endpoint. Therefore, this function, f of x, which is equal to the square root of 1 minus x squared, is continuous. Therefore, f of x is continuous from negative 1 to 1. Last thing we're going to look at today is we're going to look at something called the intermediate value theorem. Now this theorem says if you have a function that is continuous over a closed interval from a to b, so that's a requirement. We have to always check and make sure we have a continuous function on the closed interval. Then our function takes on every value between f of a and f of b on that interval. So looking at our graph here, we can see that if I plug in my endpoint A, I get f of a's. Plug in my endpoint B, I get f of b. And so if it's continuous, I'm guaranteed that I will have every y value between f of a and f of b on that function. That's the only way I can get from f of a to f of b is if I include every possible value on this interval. And that's what the intermediate value theorem says. So when we're using the intermediate value theorem, we always have to first check and make sure we have a continuous function. So let's try one. In this problem, I'm going to determine that the intermediate value theorem applies to the function on the following intervals. So first thing we have to identify is, do we have a continuous function? So I'm going to use my knowledge of these equations to determine if the function is continuous on each of these intermediate values. So always remember, to use the intermediate value theorem, we first must guarantee our function is continuous. So we look at each individual piece. We know that negative 2x plus 1 is a polynomial, and all polynomials continuous everywhere. We also know that x squared plus 1 is a polynomial, so it's continuous. And 3, the square root of x, is a rational function, and it's continuous anywhere where what's underneath the square root is positive or equal to 0, which would be any numbers greater than or equal to 0 in this case. And since that piece is only going from 1 to 4, it's continuous. And then my last one, this rational function, well, it's going to be continuous everywhere except when the denominator equals 0. And so let's check and see if that denominator is equal to 0 when, if I solve that, I end up when x is equal to 5. So that's in that piece because we're using this equation when x is greater than or equal to 4. So I have a vertical asymptote at 5. So I know I have a point of discontinuity, infinite discontinuity, at x equals 5. So I can see in my last choice here, example E, when I'm looking at the interval from 2 to 7, 5 is in that interval. So automatically I know that I cannot use the intermediate value theorem for the interval from 2 to 7 because I have a point of discontinuity at 5. So as you can see, I wrote here, the intermediate value theorem doesn't apply since f of x is discontinuous at x equals 5. Now, to look at part A, we need to figure out if the function is continuous from negative 4 to negative 2. Well, my only problem might be that endpoint negative 2. So I need to prove that it's continuous at that endpoint of negative 2. So to find the upper endpoint, I need to look at the limit as x approaches negative 2 from the left. And I get 5. Now, to do part A, I only need to know if the limit from the left is equal to the function value at that point. But I notice some of my other intervals have negative 2 in the middle, so I'm going to go ahead and make sure, see if it is continuous or discontinuous from the left and from the right. So that's what I'm going to do, work here. And I found out that the limit from the left is equal to the limit of the right, so the function value, the limit exists, and it's 5, and the function value is 5. So that means this function is continuous at negative 2. I also noticed that from the left endpoint, I have the limit as x approaches negative 2 from the left is 5, and the function value at negative 2 is also 5. So I know that the intermediate value theorem applies in interval A since the function is continuous over that entire interval, including the endpoints. For interval V, negative 3 to 0, I looked at the first two equations, which are polynomials, and they are continuous everywhere. And the pink above, I've already proved that the limit from the left of negative 2 and the limit from the right of negative 2 is equal to the function value at 2. So I know the function is continuous at that division point. So therefore, I can say by the intermediate value theorem will apply to the interval from negative 3 to 0 since the two polynomials are continuous everywhere. And at the point negative 2, the function is also continuous. Okay, let's look at interval C from negative 1 to 1. Well, I already proved earlier that the function, that polynomial function is continuous. And I know that the radical function is continuous everywhere as long as x is greater than 0. And I'm only using that equation when x is greater than 0. So all I have to do is check the endpoints of negative 1 and 1. Well, since negative 1 is within the polynomial x squared plus 1, I know it's continuous. So I actually only have to check the endpoint 1. So that means the limit from the left of 1 must equal the function value at 1. As you can see that those are different values. Therefore, I know this function is discontinuous at 1, and the intermediate value theorem does not apply. Finally, let's look at interval D, and this is from 1 to 4.5. So the only endpoint I need to check, the only value that could be discontinuous at is at 1, since I know that rational function is not discontinuous until 5, which is not in this interval. And where the function split at 4, as I just highlighted in red. So I need to make sure, let's check the continuity at x equals 4, because everything else has already been proven. So I'm going to look at the limit as x approaches 4 from the left, which would be the third equation, which is equal to 6. And we'll compare that to limit as x approaches 4 from the right, which would be the rational function, the last equation. That answer also gives me 6. And so for my third piece, I need to figure out the function value at 4. And I would use the bottom equation for that, or the last equation, and I get an answer of 6. So since my limit exists, and it's equal to 6, and my function value exists, and it's also equal to 6, I know this function is continuous at 4. So I have a function that's continuous over the entire interval from 1 to 4.5. So that means the intermediate value theorem applies in this problem. Since f of x is continuous over the entire interval, the entire closed interval from 1 to 4.5. This is only one way that you might see the intermediate value theorem. Let's look at another type of example. So in this one, we're given the function value, and we want to prove that there is a solution of f of x equals 4 on the interval from 0 to 2. So first thing I have to do is I look at my function, f of x. Well, I know x squared is a polynomial, and we know polynomials are continuous everywhere. And then I know cosine of pi x is also continuous everywhere, because the sine and cosine function are always continuous. And finally, if I take a continuous function and I add another continuous function, I know that sum is also continuous. This is one of the properties of continuity. So from that, I know that f of x is a continuous function, and I can use the intermediate value theorem. So to prove that f of x has a value equal to 4 in that interval, I need to look at the endpoints of my interval. So first I need to figure out the function value at f of 0 by substituting 0 in place of every x. And I end up with 0 plus cosine of 0, which we know from a unit circle is 1. So I know f of 0 is at a y value of 1. And then let's check the other endpoint, f of 2. Plugging that in, I end up with f of 2 as 5. So I know that my y values range from 1 up to 5. So since 4 is between 1 and 5, I know there must be at least one time on that function I have a value equal to 4. So we can say, therefore, by the intermediate value theorem, there must exist some value for x. So there must be some solution for f of x equals 4 on our interval from 0 to 2, since 4 is between 1 and 5. And f of x is a continuous function.